to tuning and optimizations, and also sharing common knowledge and troubleshooting procedures. So we have an exciting program. We have 35 speakers from 20 organizations. You can see here listed. As of today morning, we have 235 registered attendees from 154 organizations spread over 22 countries from 6 continents. Based on your organization, we have just done a best effort in identifying the countries. Due to any reason, if your country is not listed, please let us know. We'll be happy to update. So we had a great day yesterday with a set of tutorials from our sponsors. Started with AWS, then moved to the NVIDIA talk, then Rockport Networks, and we also had tutorials in the afternoon from Oracle, as well as from the MVAPICH team, going over both the HPC aspect as well as the deep learning, machine learning, and task aspects. And then we also had a tutorial and live demo from Excel Solutions. So today we have also a very packed and exciting day. We'll be starting with Keynote from Gilad Shainer very soon from NVIDIA Mellanox. After that, I'll be providing an overview of the MVAPICH project and future roadmap. We'll have a presentation from Lawrence Livermore, Adam Modi, on scalable checkpoint restart with respect to MPI. Then we'll have a presentation from Idaho National Lab on MVAPICH integration for PBS Pro. We have worked with them in the past. He will present the solutions. Then we'll have a presentation from Broadcom on their Rocky V2 congestion control evaluation, followed by presentation from Rockport Networks, Matt Williams. We are working with them, having MVAPICH on supporting on their new Rockport switchless network. So you will be hearing some of those results. And then we'll have a presentation from Microsoft Azure, MVAPICH on Azure for both HPC and AI. We'll also have a similar presentation from AWS, how MVAPICH is working there on the AWS systems. We'll have a presentation from Professor Samir Sande, focusing on MVAPICH and Tau integration. And this time we'll have a very special session here. I think some of you must have heard of it. Recently, we have been funded a very large-scale project, NSF-funded AI Institute. I'm leading it, but there are 14 universities, 46 PIs are involved. It's a $20 million grant. So we'll have a special session. It's called Icicle. So how we take HPC and AI and applications together. So we'll have a session in the afternoon for that. And then we'll have a lot of short presentations. Just like last year, I think a lot of people liked it. We'll be giving you some more detailed technical aspects into going into some of the current features of MVAPICH as well as some of the upcoming features. And then tomorrow morning, we'll have a keynote talk by Luis De Rose from Oracle, followed by presentations from Dr. Min-Sik Kim from Keynote Supercomputing Center, South Korea. After that, we'll have a presentation from Hyunwook Jin. He will be talking about energy efficiency of MPI internode communication. We'll have a presentation from University of Tennessee, Knoxville, how to accelerate communication cost on parallel 3D FFTs. Then we'll have presentation from San Diego Supercomputing Center. Mahidar Tatineni will be presenting his experiences with MVAPICH deployment on SDSC's Expanse supercomputer. So then in the afternoon tomorrow, we'll have a presentation from Todd Gamblin from Lawrence Livermore National Lab. As you know, he's leading the SPAC initiative. So we have been working very closely with him to see how to have binary distributions in the SPAC. So he will be talking about that. We are also collaborating with Red Hat. So there will be a presentation of how MVAPICH is being integrated into the Red Hat. And like the previous years, we'll also have a presentation from National Science Foundation. Dr. Alan Schussman will be talking about cyber infrastructure research, learning, and workforce development programs. And then we'll have a presentation from Excel Solutions with respect to MVAPICH DPU, and then also efficient checkpointing. And then towards the end of tomorrow, we'll have this is a tutorial and live demo again. This is along the InfiniBand Network Analysis and Monitoring, INAM, which has been deployed at the Ohio Supercomputing Center. So they will be sharing their experiences, and we'll have again another round of short presentations going into some of the futuristic things what we are working on, and then we'll have in the end an open mic and conclusion session. As you know, in the open mic session, we always like anybody can just talk, free discussion of your thoughts and comments. If you would like to indicate what works, what doesn't work with the MVAPICH library, what can be improved, suggestion for improvement, feature request, and also challenges for the MVAPICH team. So everything is entertained. And as some of you know, every year, people challenge us, the MVAPICH team, to add some new features, new capabilities, and we always try to take care of those. So we are trying to do this using the Zoom. All of you would have got the instructions. So we have disabled the chats, but please ask questions using the Q&A boxes in the Zoom webinar. And we also have dedicated Slack channels. They have been created to facilitate discussion with speakers and the topic. If you have some long discussion or longer questions, please direct those to Slack, so the speakers can answer those in an asynchronous manner. And this is the link for the Slack link you must have received also through registration. And as the presentations are happening, we are also collecting a PDF version of the slides. We are also recording the presentation, so please send all your PDF presentations to these two people, and we'll also be linking the recordings, video recordings, very soon. So in the end, I'd like to thank all our sponsors, AWS, Oracle, Rockport, NVIDIA, Excel Solutions, Paratools, Ohio Supercomputing Center, and Ohio State University. But more importantly, we'd like to thank all our keynote speakers, all other invited speakers, and most importantly, all the attendees. I mean, without the attendees, it will not be a good conference. Moderators during the virtual sessions, our webmaster, Matt Labor, and a lot of other students and staffs from the group, from the MVAPICH team, who have been working very hard over the last few months to put together this program. And special thanks I'd like to give to both Dr. Harish Subramani and Dr. Amir Safi. They have been the main organizers for this conference. So with this opening remarks, let me introduce our keynote speaker for today. Amir, I think you have the slide I'd like to share. So today's keynote talk will be presented by Gilad Shainer. I think many of you know him in the community. He is a Senior Vice President of Marketing for Mellanox Networking, and recently acquired by NVIDIA. And he joined Mellanox many years back from 2001 as a design engineer, and later served as Senior Marketing Management role since 2005. He also serves as the chairman of the HPC Advisory Council. Many of you must be familiar with that, and the president of UCF and CCIX Consortium. He is also a member of the IBTA and a contributor to the PCI SIG, PCIX, and PCI specification. He holds multiple patents in this field for high-speed networking. He's a recipient of the 2015 R&D Awards for his contributions to the Core Direct in network computing technologies, and 2019 R&D Awards for his contributions to the UCX technology. So with that kind of background, Gilad, let's welcome you to this to the MUG. So you can please share your slides and get started.
Thank you very much, DK, and I'm really honored to give a keynote in the 9th MUG conference. So I appreciate the opportunity, and definitely looking forward for hopefully next year a physical event. I miss Ohio, miss the center. So hopefully we'll be able to meet next year in person.
Sure.
I'm gonna talk about what NVIDIA is doing regarding the HPC network that we develop. As you mentioned, I was with Mellanox for a long time, and now a year and a half, I think, give or take, at NVIDIA. And it's very interesting to actually work in a place that build not components in that sense, but actually build a full computing platform. So we're looking at computing engines, we're looking at the networking engines, we're looking on the SDKs that brings everything together, the full software stack, and go all the way to the application perspective. And it's a unique opportunity to actually build a system or optimize a system from all levels, coming from the software side into the hardware side, from the hardware to the software side. Look on the full platform, look on a full stack. And obviously the most important part is how fast we can run applications, how we can enable to run problems that we couldn't do before, and how we have the ability to take an holistic view on the entire system and understand where each of the compute algorithms that we're executing, which will be the optimal place for that algorithm to run. So it's amazing, right? It's amazing, right? So first, I'd like to kind of take a full view on the platform, full view on the scientific computing. And I think there is several trends that actually driving progress, driving development. First, there is a change in the platform itself, meaning if in the past, when we talked about supercomputing, we talked about a system that runs a job or some jobs, but everything was contained in that system. Now, actually, the world of scientific computing is extended beyond the supercomputer, beyond the one system. We're going all the way to the edge. And we're developing today framework for edge computing to bring compute capabilities to the places we source data, to bring computing capabilities to the instruments that we're running our experiences on, and take results of experiences and run that through frameworks and potentially be able to give indications to modify or change the experiment as needed at the edge. And from the edge, to be able to move the data at the same capabilities that we have inside of the supercomputer, meaning ability to actually have InfiniBand at the edge and run native RDMA, have the same full management view all the way to the main system or to the storage and so forth, and do another analysis there, which can actually go and drive changes into the experiments that we're doing at the edge. So it's not just running inside of the supercomputer, it's actually going all the way to the edge and having the framework at the edge that's connected to the main system. We also have the need to go and start bringing cloud services into supercomputing. I'm going to touch about that as well. And that's because HPC is essentially going everywhere. HPC will go to places where people didn't use HPC before. And deep learning and AI will go into more places because that's going to help us in a lot of applications. And if AI is going everywhere, then HPC is going everywhere. That means that there will be more applications and more users that are utilizing HPC. So we need to support growing amount of users. We need to support growing amount of applications, ranging from real-time processing to simulations to training. Digital twins. Digital twins, you can actually have a complete mimic of something that exists and see how changes there can affect the other side or the real side. Visualization, there are many applications here. NLP is natural language processing, and recommenders and so forth. More applications, more users. We need the ability to start bringing multi-tenancy support into supercomputing. And we need to do it in a smart way because we don't want to impact the bare metal performance of supercomputers. So we need to find a way to bring multi-tenancy into supercomputers and keep bare metal performance. We need to be able to go all the way to the edge and connect the edge in a same view and have the same view of the complete supercomputer at the edge, so we can control everything from one place. There's a lot of interesting development around that, and we bring more capabilities into our computing platforms that actually cover those two sides, going from the main system to the edge, as well as supporting the growing amount of application, the growing amount of users. So if I just do a quick overview of what are the components that we're building, what are the components that build the network framework, and then that framework integrated into the compute framework. So to connect things together, computers and storage and so forth, there are the two kinds of actually network adapters. There is the ConnectX family, and then there is the DPU, the data processing unit. And I'll talk more about the DPU down the road, but the DPU, it's a silicon device that first includes all of the NIC functionality. So the entire ConnectX network adapter exists in that Bluefield DPU silicon. But beyond that, there is also multiple ARM cores inside of that silicon device, and different kind of acceleration engines and security engines and infrastructure engines and a memory. So it's essentially, it's a full data center on a chip that provide all the networking services on one side, but on the other side, bring us capabilities of further accelerations, bring us capabilities to migrate the infrastructure workload, the infrastructure operating system to the network device and free the CPU cycles and bring security, multi-tenancy, and a lot of great things. And I'll talk about it. And then we have the switch that connects everything together. The switch is actually an important element, meaning you can take multiple adapters and just connect them together, and that's fine. But there are elements of the network that are very important as you want to scale. The ability to deal with different kind of routing schemes and congestion management and build different kind of topologies that can provide great capabilities at small scale and at large scale. Building toruses, it's a great element for stencil application. It's a really bad idea if you're looking on a broader range of applications. So you want the ability to do the factories and the dragonflies and maybe the toruses and the HyperX and other topologies, match topologies to what you build. And on the other side, there are multiple computing algorithms that the ideal place for them to be executed is on a switch, not on the server, not on the node, not on the adapter, on the switch. And that's because the switch connects to all of the nodes together, and it can do multi-process algorithms faster and more effective than anything else. So building infrastructures that the switch doesn't really exist, or it's not a smart device, it's not the right direction moving forward in that sense. On top of those elements, there are multiple appliances that bring extra capabilities. On the left side, there is an appliance that calls MetroX, and that enables to extend the native InfiniBand connectivity, the native RDMA connectivity, the in-network computing capabilities, and so forth over long distances, which enable us to connect the main system to the edge, to connect the main system to the labs, to connect the main system to the instruments that are running the experiments, to the edge, and then moving data from the edge very effectively, bypassing CPUs, enabling the same management view of a supercomputer to be extended all the way to the edge. and bring those capabilities. So Metro X is a key enablement for connecting the edge into the main system, into the supercomputer. Skyway, it's a gateway that seamlessly connects between InfiniBand and Ethernet. And there is always debate, I want to use Ethernet, I want to use InfiniBand, and so forth. At the end of the day, InfiniBand is the most advanced technology for high-performance computing. That's why we decided to use that technologies in the superpods that we built, for example, which provide the best performance for both HPC and AI. And InfiniBand is being used more and more in other applications. Obviously in the HPC space, but it's becoming the de facto for AI, for deep learning. It's strongly adopted by a lot of the the big cloud vendors out there. We know the public examples of Microsoft Azure that are using InfiniBand for HPC clouds. But we also have InfiniBand in Facebook, we have InfiniBand in Alibaba, we have InfiniBand in Baidu, we have InfiniBand in others, which actually adopting more and more InfiniBand because of its capabilities. InfiniBand is also being used in financial services, in payment services, in other areas because of its advantages. And then you want to have something simple, effective to connect InfiniBand to the outside world. And this is exactly what Skyway does. It has multiple ports of InfiniBand and multiple ports of Ethernet, and it seamlessly connects between the two sides. And it's the most effective way to connect Ethernet into the main system and keeping the main system running in the best performance, lowest latency, and with no impact, no overhead because of connecting to Ethernet. And then last and not least, UFM Cyber AI appliance. The UFM, it's an appliance that brings capabilities or simple capabilities, or simplified actually, the management, the orchestration, the monitoring of the network, to be able to do a profiling of the system. But it's more than that. It's more than that. The UFM Cyber AI, it's an appliance that also collects telemetry information from the network, from switches, adapters, cables, transceivers, and so forth. And it builds an historical database of telemetry information on which it runs deep learning algorithms to identify anomalies in usage of the network, anomalies in usage of the data center, which indicate security threats. He looks for performance degradations over time and create correlations between different kind of events, which brings us the ability of predictive maintenance, ability to foresee failures before they actually happen and deal with them and fix them and take the right action before something fell in the system. So it bringing great elements from a security perspective as well as from predictive maintenance. Now, when we look on a network, especially when we look on InfiniBand, but when we look on a network, the network needs to provide not just networking services. In the past, we looked on the network as a pipe that moved data from one side to another side, meaning just providing network services. And InfiniBand excels in that. So if you look on InfiniBand side, it provides the highest throughput in the market today. It's running 200 gigabit per second for more than 2 years. And in next 2 months, we're moving to the 400 gigabit per second generation. So we're going to move data in a speeds of 400 gigabit per second per port. And if we look on our supercomputers, disaggregated supercomputers, variety of applications, variety of users, the more bandwidth you have, the better you are. Extremely low latency. And it's not just the ping pong latency. We're talking about even the more complicated algorithm latencies. There is nothing that get close to InfiniBand in that sense. Message rate and so forth. InfiniBand also pioneered RDMA. And RDMA was copied into Ethernet, which was what we know about Rocky, and obviously NVIDIA is doing the best Rocky out there. But InfiniBand provided most efficient data movement with its RDMA, better than Rocky. And definitely on the latency perspective. And InfiniBand has an RDMA capabilities to move data directly to the CPU memory, to the GPU memory, from the storage to the GPU memory. So all the options from that perspective. And there is the adaptive routing and congestion controls and quality of service and different approaches and so forth. And we talked about, by the way, we talked about adaptive routing, congestion control just as examples. But this is not enough. When we look on a networking for HPC platforms, we need to actually have also compute services coming from the network. We cannot continue with the old idea that we need to move data all the way to the compute before we can do something on it. We actually need to move compute to where the data is. That's why we're doing edge computing. And moving compute to where the data is means that we need to move compute to where the network is. And from two reasons. One reason is that, again, there are applications or algorithms that the ideal place to be executed is on the network. And nothing you will do on the host will get close to what the network can provide if you're running that algorithm on the network components. And the other side, we're also bringing programmable engines into the network, and those programmable engines bring us ability to add more services to supercomputing while maintaining bare metal performance. So the network cannot be just element that move data from one side to another side. The network becomes very smart. There are computing services from the network. There are networking services from the network. And that's how the network becomes more advanced, or actually enable a more advanced, a full compute infrastructure, a full stack infrastructure. So if we look on examples, I decided to start with the GPU Direct RDMA, just as an example from an RDMA perspective. And GPU Direct RDMA was created back then by Mellanox and NVIDIA, which is now one company, to eliminate buffer copies and take out the CPU from being a bottleneck in the path of moving data directly to the GPU memory. And we were very happy to work with Professor Panda and his team to bring those capabilities and demonstrate that by having the network moving data directly to GPU memory, we can increase the performance of GPU operations by 10x, reducing latencies by 10x, improving bandwidth by 10x, and so forth. Now, when we look on RDMA, there are two networks that actually gives RDMA capabilities. One of them is InfiniBand, the other one is Ethernet with Rocky. No other network has actually RDMA there. The proprietary networks don't include RDMA support. First, probably because RDMA is not simple to add. And second, because they're not trying to serve both compute and storage applications in that sense. So here we're comparing InfiniBand to Rocky, and we're looking on Rocky on NVIDIA side. And if you're going to run Rocky on other companies' devices, we're probably going to see even much worse performance. But you can see that even with no switch in the middle, just a node to node connecting directly, InfiniBand it's faster. It's around 7% faster. And once you start bringing switches into the game, it's a different game. With just a single switch, we're going to 30% performance difference. You have more than one switch, the gap is big and bigger, and that's one of the advantages of InfiniBand on providing the lowest possible latency. We can see the effect, for example, on applications, and I took an example from something recently that was run, Nickel, which is the NVIDIA communication library in Barrett, which is part of NLP, natural language processing, and you can see that just RDMA, just RDMA, doing RDMA over InfiniBand versus RDMA over Rocky, there is a big gap there on the application perspective. You know, we're looking at 16% performance gain on the entire data set. And that's just RDMA to RDMA, nothing else. No computing engines, no network computing, just RDMA to RDMA. Now, other parts of networking services are, for example, adaptive routing or congestion control. And adaptive routing is a way to solve congestions that happen from point-to-point communications. And InfiniBand has adaptive routing, fine-grained adaptive routing that enables actually to spread the traffic as even as possible, and utilizing all the network paths that exist. On the other part, those are results that were tested previously on Summit, comparing static routing to adaptive routing on MPI graph. And with static routing, we can see that there are MPI pairs that sharing the same path, and that's why they're getting less network bandwidth or less network efficiency. And there is some pairs that gets higher efficiencies because they were lucky enough to not to share the path with any other pair. With adaptive routing, the network actually spread the traffic. So you get a very nice histograms, you get nearly 100% of network efficiencies, and the network actually spread the traffic as even as possible in utilizing all the traffic, all the network paths for the traffic. We can also see the impact of that on applications. VAS, for example, gains 10%. 10% performance increase once running with adaptive routing, and BSM bench, it's going to the 25, 26, 27% performance gain. Again, just moving to adaptive routing and let the network spread the traffic as even as possible. The other side of things is congestion control. And congestion control has evolved over time. And if the past, for example, in the past years ago, people looks on congestion control, kind of solving the many-to-one, solving the cases of buffers that get full because of many-to-one and creating victim flows. Years ago, options were dropping packets or dropping data in order to free the buffers. Later on, it becomes a technology that you can mark information and so forth, and then have the endpoints throttle the data or throttle their speeds so they avoid congestions. Now we're actually moving to much more advanced, which I haven't seen from anyone to date, and that are unique capabilities that NVIDIA is bringing, which is actually using real live and telemetry information into a smart end-to-end elements, all right, smart end-to-end congestion control. So we're going to talk more about that later this year, about those unique capabilities, which moving us to completely new capabilities of avoiding congestion with not reacting to situation, but actually understanding things based on telemetry, based on sensors, based on different elements that sense, and doing an end-to-end mechanisms. Here an example, by the way, of congestion control running on an HDR platform. This setup has 8 nodes and a couple of switches here that connect things together. And we're going to run it twice, with congestion control, without congestion control. So in this case, everything runs in 100 gigabit per second speed, and we start with running one flow number A, that connects moving from node 3 to node 4. Obviously, it gets 100 gigabit per second. Then we're adding a second one. We're adding a second flow. A and B share the same 100 gigabit per second link. And the 4, obviously, both of them is going to get equal shares of the path, and the 50 gigabit per second each. Now we're going to add another one, another flow, another 100 gigabit per second flow. And now we're moving to a scenario where both C and B sharing a link between the two switches. So essentially it's 50 gig each. B also share the same path with A, and therefore you should go to an equal, or keep the 50 gigabit per second, which you see more or less that's what happened. And now we are going to add another flow, flow marked as D. And now it's becoming interesting. So first, we create many-to-one. So if previously B and C were 50 gig, and node number 8 could get 100 gigs. So there is no back pressure in that sense. Now we actually have 3 flows that goes all the way, and then they can send more than one. 8 can do. So now you started getting pressure here. Now on this link here between the switches, we have 3 flows. So essentially each one of them should get 1/3 of the 100 gigabit per second. So it should be 33 gigabit per second each, which means B needs to be 33% or 33 gigabit per second as well. That means that A, in this case, can go up to 66. But because of the back pressure and so forth, what's actually happened without congestion control is that A also suffers, because A will move if B will move, and B moves in a cadence of 1/3. And therefore also A gets the cadence of 1/3 in progress, and A becomes the victim flow in this case. And with congestion control, you see that there is a very fast convergence, and then A gets to the 66% of the 100 gigabit per second, or 66 gigabit per second. And then D, B, and C actually get their share, the equal share between them. So that's an example. We can look at another example. In this case, looking on GPC net benchmark performance. And here, actually giving you the two views. So on the left side, from the 3 cases, you're looking on the random ring latency case, running the random ring latency case in an isolated mode, which means that's the only thing that is running. And it's running at a 1 microsecond. It's actually 1.1 microsecond latency. And then running the random ring latency with the presence of the noise, with the background noise, no congestion control. And we can see that actually the performance of random ring latency gets 7x worse, give or take. And it's around 7 microsecond latency. And then with infinite band congestion control, get the sensing, runs end to end from that perspective. It's you get back to the ideal performance of random ring latency. You have the 1.1 microsecond latency with the presence of the noise. Now it's also important to look on the worst case scenarios. Looking on the worst case scenarios, 99%, which means what's the tail latency from that perspective. And you can see that here, comparing random ring latency and or reduced latency, the 2 latency benchmarks as part of GPCnet, and comparing that to a proprietary network that mark congestion control as one of their highlights. And you can see that on the random ring latency, looking on the 99%, on the worst case scenario, we're looking on a 3x difference here. Looking at 3x difference here, and this is the ratio. So it's a 3x difference here. If you look on all reduced capabilities, we're talking about 11x difference. 11x difference. And of course, one of the elements that enable the InfiniBand all reduced operations to be very low, it's the ability of doing reductions on the network. It's the ability to run the all reduced algorithm on the switch network. And that's why you need computing on the network. That actually takes me to the in-network computing engines. So we covered the network services. RDMA is key, definitely key for storage, bypassing the CPU and so forth. And there is adaptive routing on one side and congestion control on the other side. And then there are the computing engines, in-network computing capabilities. And data reduction is one of the algorithms that running it on an endpoint, it's a big mistake. If you're running that on an endpoint, you need to move data all the way to the endpoint to do the reductions, which means the bigger the system is, it's the higher the latencies. Regardless, what's the latency on the network? You need to move more and more data if you grow the system size. And you cannot actually get out of that performance bottleneck if you're running reductions on the node. No way. The only way to get to a single digit of latency of microsecond for reduction operations, to keep it flat latencies, to reduce data motion, it's moving the reductions to be executed on a switch device. On a device that connects to all of the nodes in that sense and enables the nodes to send data to the switch does the reduction and does send the response back. And on the network, we support multiple integer and floating point sizes for the different applications. And there is some other new aspects that are going to be introduced, by the way, with NDR generation later this year, which we'll probably talk once we reveal those towards the end of the year. Now, the network enables, or the switch network enables, to build reduction trees in different ways, and the reduction tree can cover some switches, cannot cover some switches. You can have multiple switches serves as a reduction element for different kind of trees, different kind of job trees, and so forth. So you have the full flexibility from that perspective. And doing reduction on the network, which means you need compute on the switch, which means you need the switches for running those things, for example, give you flat latencies. Doing reduction on an endpoint means that the more endpoints I have, the higher the latency is. Doing reduction on a NIC means that the more NICs I have, the more nodes I have, the higher the latency is. Doing reduction on a switch network means that you get flat latencies because the switch network is much more immune to the system size. And you get the reductions in data motions and other things. We incorporated Sharp, which is the reduction of the network, into Nickel, into the NVIDIA communication library, and actually we're able to improve Nickel performance by 2.5x. And this is critical for deep learning frameworks, for example, of moving the large or doing reductions for large messages, very large messages. And if we look on InfiniBand versus Rocky, for example, on the same operations, first, InfiniBand is running faster than Rocky. Small messages, there is a big gap. Large messages, there is a smaller gap percentage-wise, but InfiniBand is always run faster. And then once you bring Sharp into the game, which is an InfiniBand advantage, you're talking about more than 4x difference. So that's another reason. Another example of in-network computing engines or computing capabilities that the network provides is running NPI Tag Matching. So NPI Tag Matching mechanism, if you do it on a CPU, it means that every time you get an incoming NPI message, there will be an interrupt generated, and the CPU will need to do a buffer matching and figure out where to write the data to. In InfiniBand case, actually the matching is done on the network device, and the network device get the list of posted buffers, the matching, and if there is a match, it will scatter the data to the local buffer, or actually can do the full rendezvous protocol. Unexpected messages will go to the CPU in that case to be handled and covered there. But if the data comes and there is a posted buffer waiting for that, the operations will completely be done on the network. So here there is a table where we try to do something which is more artificial. All the in-network computing engines are actually working as one unit. So if you're running an MPI job, you have the tag matching part, and there's the reduction part, and so forth. So each one of them fuel the other. We try to isolate each of them and look separately of what would be the impact of just that engine disabling everything else on some applications, and what would be the gain of them. So on the reduction of the network, the switches can do small message reduction, which is classical HPC, and large message reduction, which is classical AI from that perspective. And small message reduction, we're reducing the latency of all reducer portion by 7x. That reduces total MPI time of different applications by 25 to 30%, which in return, looking at 15% of application performance, full application performance. So just having reductions on the switches, can impact the data center in a full 15% on entire data center performance. An open form or deal poly or Reliant, those are 3 examples. Large message reduction on HDR, improved nickel performance by 2.5x. And then when we take it to the full application, the full data center performance, demonstrated 15%. And those, by the way, they were demonstrated by some of the large hyperscale companies out there. 15% faster recommenders, 50% faster deep learning recommendations, which is critical. 15% gain on my entire data center. 17% faster natural language processing. You can do things much faster just because of running reductions on the network. Tag matching, obviously improve overlapping between compute and communication, and we're seeing impact on different applications. It's all the way to 40%. Can impact all the way to 40%. With the upcoming generation of InfiniBand, which is called NDR, the 400 gigabit per second device, we're bringing new capabilities of doing small message all-to-all in the network. That will improve the throughput of all-to-all by 4 to 5x. And obviously later this year, we'll start running applications and look on the impact of that specific engine on application perspective. So, talked about network services, talked about computing services. Now let's talk about the DPU. Let's talk about the data processing unit. So the DPU, it's a silicon device that includes all of the network adapter inside. So in the case of Bluefield 2 here, there is a full ConnectX-6 inside of that silicon device, instead of that Bluefield DPU silicon device. Now, beyond of all the network functionality here, there's also multiple ARM cores. Multiple ARM cores, 8 cores of ARM A72 in the Bluefield 2 case, more acceleration engines. So we have the all-to-all engines and the other engines as part of the ConnectX, for example. But here we're bringing security engines and file system engines and infrastructure service engines and so forth, as well as memory interface. So there is a memory on the card and a PCI Express switch, so you can connect a PCI Express device directly to the DPU, which could be a GPU device if you need more performance or more compute next to the DPU. Could be flash devices, put more memory on it. The DPU here, this device is serving 3 applications in that. It's serving 3 applications. One application is edge computing. I want to bring compute to my sensor. I want to bring computer to my instrument. The DPU is a full data center on a chip. So I can bring one DPU there and actually have the compute part and then be able to actually send the data out. Or I can have a collections of DPUs or collections of DPUs and GPUs, for example. And it's much beyond HPC. You know, DPU goes into 5G network, for example, and so forth. Again, the same target as for edge computing. Within the data center, there are two areas that the DPU is meant for. One is to run the infrastructure workload, to run the infrastructure management, the data center operating system. I mentioned before that we're going to see more applications and more users running on HPC, running on a supercomputer. More users, more applications. We need to bring cloud services because we need to isolate between those users. We need to isolate between those tenants. We need to bring security between those tenants. We need to move our supercomputer toward a zero trust architecture. And doing so means that we are bringing more overhead, and the infrastructure workloads become one of the more complicated workloads that we need to deal with. And if we're going to run those workloads or the infrastructure workloads on the CPU, we're going to reduce the CPU performance, and we're going to get a much lower bare metal performance from our supercomputer, which was built in order to give us the best possible performance. So that's why we need to have a different or another engine that can deal with the infrastructure workload, and this is what the DPU meant for. So the DPU enables us to migrate the infrastructure workload, the file system management, cluster file system, network file system, moving the security in isolation, and run those on the DPU instead of doing that on a CPU. And by doing that, we can actually maintain bare metal performance while bringing a multi-tenant isolation together. And that's one of the great values of the DPU. Now, as we bring the DPU, and the DPU now runs the infrastructure workload, we can also use the DPU as a new accelerator in our system. We actually have a computer inside of the computer. We have a computer in front of the computer, which we can use in order to do interesting things. So we have a new accelerator. We are moving to a new hybrid model of a GPU, CPU, DPU. And it's going to change the services that we can get from our supercomputer in that sense, as well as its performance capabilities. So by moving, by the way, the management, the monitoring, isolations, the file system from the host into the DPU, there are more resources for the applications. Actually, the DPU is the better place to run security on. Doing security on the CPU means that we're running security in isolations on an untrusted domain, because it's the same domain that runs the applications. So moving the multi-tenancy into the DPU means that we're running the multi-tenancy and security on a trusted domain, which is a much better domain to run all those services on. And looking on the security part of things, the DPU enables us to move our supercomputer towards a zero trust supercomputer or zero trust architecture. So the users are running on the host and they are quote unquote locked in that host and they cannot impact outside. Everything goes through the DPU in that sense, and the DPU actually does the full provision of the server. It loads clean operating systems, it deletes residual information, it does the full provisioning of the system and do the full isolations between the users, between the jobs. And file system, it's the same thing. Instead of in the DPU case, the file system or the DPU actually is the file system for the jobs. And the job of the user will mount storage on the DPU. And the DPU will do the mounting of the storage on the file system, so you can control which user goes to where. So we're moving toward a zero trust architecture. We can host more users, we can isolate between users. We can have our supercomputing resources be better used by industry partners, for example, or be able to run analysis of private information or medical information, creating encrypted enclaves or protected enclaves within a supercomputer to run confidential information there, do simulations on confidential information. And then on the network itself, full isolations on the network itself. And with InfiniBand network, we can isolate 32,000 concurrent users same time. Probably more than enough. Now, as we have that part, we can do even more things with the DPU. More things with the DPU. We have announced a framework called Morpheus AI Cyber Security Framework. This framework is trained to look for anomalies on data being sent on the wire, on the network. One simple example, let's say that we are building a system, we build a system, we give access, and there is some sensitive information there, and we want to make sure that all information is supposed to go encrypted. All non-encrypted data going out kind of in the open will be monitored by the DPU and will be sent to the Morpheus framework that it's running on an appliance, running on a system. That framework is trained to look for sensitive information, username, passwords, other things. And if you get a detection of personal or sensitive information being sent in the open, Morpheus will provide immediate indications to the DPU to shut down that server. So you can have a real-time monitoring that does not impact the performance. It doesn't create an overhead. It does by the DPU. And then you are able to actually control. And if you need to shut down a server, you're going to shut down the server. And make sure that there is no sensitive data that is going to be sent outside. So there's a lot of interesting things that you can use the DPU as part of security, as part of supporting multi-tenant and isolation on a data center or supercomputer. Now, as we're bringing the DPU here in the game, we can use it to accelerate things. And you can run processes on the DPU that can form or execute RDMA operations locally and remotely. And you can migrate work from the host into the DPU and have the DPU progress things by itself. One of the obvious things to move into the DPU is collective operations, non-blocking operations. Migrating non-blocking operations to the DPU means that we can get to a full overlapping between computing and communications. We can run things more effectively. We can improve application performance. But it's not just there. You can use the DPU for active messages, for NPI progression, for any sort of user-defined algorithms. We are moving towards a new hybrid model where you have a GPU, CPU, and a DPU, and computing engines on the switch devices as well. So you get computing everywhere. And now you can figure out where is the right place for me to run which algorithm. So here there are some graphs that I borrowed from DK, and I'm sure that he has an update, and I'm going to use some of the graphs. But examples of migrating non-blocking all-to-all and non-blocking all-gather from the host to the DPU and achieve performance gains. That means that we're moving to full overlapping between compute and communications, 100% overlapping. The DPU will progress the work while the CPU continue to do other works, and one of the examples of performance improvement is FFTs. And the team, MVAPICH and Scalable Solution teams actually modify the three-dimensional FFT to utilize non-blocking all-to-all and get a great performance boost just by moving all-to-all to run on the DPU. So this is just the tip of an iceberg, just an example. Now, as I mentioned before, we have the DPU that also enable us to do more interesting things at the edge. So we have the DPU inside of the data center. So that's enabling the infrastructure workload to run there and enabling to accelerate the work. But the DPU is a great edge device. And it could be a combination of the DPU with GPUs and so forth at the edge. And then we're using the long haul, the InfiniBand long haul device to can move data from the edge, native RDMA, could be secured RDMA, all the way to the main system. And since you have InfiniBand at the edge, all the way to the InfiniBand in the main system, you can actually have one big view, one central view, one management view from the supercomputer to the edge. You can think about the edge or the satellites of the supercomputer. So having one network that connects everything means that all of the compute engines on the supercomputer can see the edge. And the edge can see all of the compute engines inside of the supercomputer. It's a great advantage, and we'll see more information around that later this year. There is multiple partner of us that already using the metrics from connecting different systems on campus, remote HPC systems, HP system to remote storage, for example, and so forth. So there is multiple installations of metrics in multiple places. even beyond HPC, to synchronize between remote databases. So there is Payment Institute, for example, Financial Institute, they're using Metrix for long distance connectivity to synchronize between the databases. And now we're going to the edge, and we're connecting the instruments, enabling to connect the instruments all the way to the main system. And in order to expose the DPU services in a very simple way, in a way that guarantees that any application running on one generation of the DPU will run on the next generation of the DPU and the generation after. We've created the software development kit called Docker, which is also runtime. And Docker exposes the services of the DPU to the applications running on top of that. It does that as security services, networking services, telemetry services, acceleration services, and so forth, exposed from Docker. So you can think about Docker as the driver of the DPU and expose the services to all the applications running on top of that. So we have done first releases of Docker already, and throughout the year and obviously in the future, we'll see more capabilities coming into Docker and enabling more services coming from the DPU. So looking ahead, there is a nice roadmap of InfiniBand generations. We have the 200 gigabit per second, more than 2 years in production now. And this year we are excited to see NDR. We're going to start getting NDR devices very shortly out there, moving the world to 400 gigabit per second. And then 2 years from now, 2 years, we're going to move towards the 800 gigabit per second. And I think this is the fast cadence. This is what we need. Other company may think about 400 gigabit per second in the 2023 timeframe. It's not going to be enough. We need to move much faster. In the disaggregated world, disaggregated services in the application that we're seeing, you need very fast networks. You need very fast networks to drive the capabilities, to drive the performance. And since InfiniBand, it's a standard technology in that sense, everything is backward compatible and forward compatible. The system that you have now, you know for sure it's connected to the next generation. We have multiple systems out there that are using 3 generations in one system. Works greatly. Software runs across everything there. So what's coming? What's coming with NDR? So first, ConnectX-7 adapter with PCI Express Gen 5. So ready to the next generation of CPUs, GPUs with PCI Express Gen 5. The Bluefield 3 DPU. So 400 gigabit per second, 5x the compute capacity on it. 5x the compute capacity on it compares to Bluefield 2 with Gen 5 as well. And then Quantum 2 switch. So first, increasing the radix by 3x. 64 ports of 400 and 128 ports of 200 gigabit per second in one silicon device. And going to the 3rd generation of Sharp. More computing capabilities on the switch devices to enable us, or to enable more computing engines, more in-network computing engines for more users, for the multi-tenant supercomputer, for the cloud-native supercomputer. So moving to 400 gigabit per second, obviously 2x the bandwidth, and then there is 32x more services, more in-network computing services on the network, on the switch network. With the increase of radix, Dragonfly Plus, you do the 3 hops, you can connect more than 1 million endpoints at 400 gigabit per second each. And then we're building different kind of switch sizes, by the way, that can form different kind of topologies, obviously. Capabilities perspective, this is what we see today, and NDR will take it to the next level. So today we have the 15% performance improvement because of the compute on the switch. The entire data center is working 15% faster for commanders, 17% faster for NLPs, and 15% for CFDs. And NDR will reduce the power consumption of the network by 36%. It's a win-win-win-win situation in that sense with 400 gigabit per second. And then there is multiple building blocks. There are the simple 1U building blocks, 128 ports of 200, one switch that connect actually a nice amount of servers together. And then forming 3 classes of larger switches all the way to a 2K ports of 400 or 4K ports of 200 that will fuel the next generation of some of the exascale infrastructure out there, both industrial and research side of things. Systems are growing in sizes. People are looking for flat networks as much as possible. No toruses, no 3D toruses, no 6D toruses. They're looking for flat networks in that sense. And increasing in radix actually enables to have a flat network, 2 tiers to connect a good amount of compute on it. So this is where we're heading. Those are the excitement things. First, the DPU. Combining network functions and programmable computing and infrastructure engines and security engines and other acceleration engines to enable or to migrate the infrastructure workload as well as accelerate more things, more capabilities on the endpoint side of things. The Docker, which enables the services out, and the NDR quantum platforms that bring us first in-network computing on the network. It's a key thing, it's a critical thing, as well as all the advanced services, network services, congestions, adaptive routing, building different kind of topologies, quality of service, and so forth. And having an end-to-end view here, having a sensing of what's happening in different places, enables to build flat networks in a very effective way, to actually bring the lowest latency in a sense, but not just the ping pong latency, but actually the complicated algorithms from latency perspective out there. So exciting. NDR is going to be released very shortly. And we do hope to see first NDR systems actually built this year, and maybe they're going to be on November list. We really hope so. So with that, I want to thank you for listening, and I'm happy to answer questions if there are any.
Yeah, Gilad, thanks a lot for a very insightful talk. A lot of technology is out there. I think the people are pushing the edge. There are a lot of questions on the Slack. For you, might be I'll ask few things, and then we can do offline. So what sort of AI features does UFM have? What does it use in the back end? Gilad, you are muted. Yeah.
Oh, sorry. No, I was trying to see if I can log into Slack, but sorry, I would go with your questions. You can list them. What I missed the first part.
What sort of AI features does UFM have? What does it use in the back end?
Yeah, so UFM collects telemetry information from the data center. So network devices goes all the way to the CPU, GPU, and so forth. And it builds the historical database on that telemetry information. And UFM has a GPU inside. So the GPU actually is trained on the telemetry information. First, it's pre-trained because we have collected a lot of information from other data centers around the world, as well as connected to the local data center. It's continued to train itself. There are several things. So there is elements that the GPU is trained on. One is to look for anomalies. So it learns the kind of the heartbeat of the data center. It learns how the network behaves. And it's looking for anomalies, something new. The network is behaving differently. And that actually drives a security alert, meaning there is new application running on the data center. Something is running that in a different way. It could be that so far we were running CFD codes in a normal way, and suddenly someone is doing Bitcoin mining on it. So you get a different, you get anomalies detection. The other part is that it's looking for performance degradations over time. And it has the sensor that goes even into every lane inside of the cable. And once it detects the performance degradation over time, it looks for correlations of event and comparing to knowledge being learned in other places. So it can give you a prediction that that device is probably going to fail in 2 weeks. So you better want to look on that or replace it, or we can avoid using that path so you can replace it while continue to make sure that everything else is running. There is also a framework that is actually trained to look for sensitive information. As I mentioned, right? You can actually collect data that comes and runs in the open and then look for passwords. There is a framework that is trained to look for passwords and usernames and those kind of conventions. And if there is information that goes, sensitive information that goes out public, on the public, as open, you can actually indicate the network to shut down nodes, shut down servers in order to avoid that leakage. So there's multiple capabilities there. This is on a nutshell.
Okay, thank you. Let me go through one or two more questions, and might be either Hari or Amir, you can send the Slack pointer to Gilad, he can log on. So will in-network technology like SHARP work on Rocky?
No, the answer is no. The answer is no. SHARP runs on InfiniBand.
Okay.
And the reason that you can do more things on InfiniBand is because InfiniBand is a very simple network. Very simple network. Switches are very simple, right? If I look on Ethernet switch, typically every Ethernet switch comes with a server inside of the switch to run the network operating system of the switch. InfiniBand doesn't need anything of that sort. It's a very simple, it's very scalable, which means that if you look on a silicon device, you have more room to put more registers. And if you put the registers in a right position, you can actually add interesting capabilities into that. And one of the capabilities is compute. And this is what forms SHARP and from others compute engines that we can put on a switch fabric. And those elements or those engines are actually enabling running algorithms in their ideal situation or ideal place. So SHARP, it's InfiniBand element. It's not a Rocky element.
Okay. With personalized operations all-to-all, what benefit do you think network offloading can provide?
With, I missed the first part, with the engine of
all-to-all involves personalized messages.
Yeah.
Will the network offloading help?
So I'm going to stay a little bit in a high level just because those devices are going to come out shortly, and we're probably going to talk more about it once it's out. But migrating small message all-to-all to the network means that we can actually run small message in much higher throughput than doing that on the endpoint. I mentioned 4 to 5x. I think we're probably going to add in 7 and 8x. Which means the capability of the all-to-all throughput, it's much higher than doing things on a CPU on an endpoint. Now you can also improve performance by the way of vector, all-to-all V, and you can do some other things with other engine that exists on the network. But I'm going to keep it at that point. Okay, and later this year we'll provide more information about it.
Okay, one more question. I think the last question we'll take. Other we can discuss offline. Can you please discuss some use cases of deploying Open vSwitch on NVIDIA Mellanox DPUs? Does any cloud infrastructure use such configuration? OVS running over DPUs.
Yeah, OVS. Yeah, this is kind of going away from the classical HPC environment in that sense, right? And going to OVS, and it's more enterprise infrastructures and so forth. And OVS, yes, it's actually reducing overhead on one side, and you don't need to go into the physical switch in order to do the changing data or sending data between virtual machines, for example, and so forth. And since you run things on the DPU itself, you don't need to do there is no overhead on the CPUs or other components. So that's one of the advantages of that. By the way, if we do touch things beyond the classical supercomputer environment and so forth, VMware, for example, it's also working on the DPU. So they're actually migrating and moving their management element to run on the DPU instead of doing that on a CPU. One, the DPU is a trusted domain. It's not the domain that runs the application. So by moving all the things into the trusted domain, you're much more secured. The other thing is by using the DPU, you free the CPU from all the overhead, right? So now you have more capabilities on the CPU, or more services that the CPU can give you, and then you run all the management of the infrastructure on the DPU. So it's the OVS, it's VMware management elements, and many others.
Thank you. So I think there are still some more questions, Gilad, just to remain on schedule. If you don't mind, please log into the Slack, and then you can answer those questions. Okay. So let's again give a big hand to Gilad for his keynote talk. So we'll